So in order to show you diffraction tomography, we have to do Field approximation. I'm just going to show you the scalar form because it's a lot easier to show the scalar form. The vector form is similar but a little bit more complicated. Okay, so what is Field approximation? Say if you have an equation where k squared is a function of position, then you need to solve this equation with a certain source. As we know, we can formulate this in terms of the volume integral equation. So let me see what notation I use here. Say we can rewrite this in terms of a background, which is a constant. And then I can put whatever that is not there before. Onto the right hand side, and then put back the source term. Okay? It's just a rewriting of the first equation so that the left hand side has a Green's function. Let's assume that my Green's function satisfies this equation. You can immediately write down the solution to the second equation by the principle of linear superposition. You treat everything as a source term. Okay, then you can write down phi r as the convolution of this Green's function with this source. So it's the r prime g of r minus r prime k squared minus k naught squared g of r prime. And maybe you can also put an r prime in here to denote the fact that this k squared is a function of position. And then minus the r prime, g r minus r prime, s of r prime. This is just a statement of the principle of linear superposition. These are the sources I have. If I have this Green's function operating on these sources, I get this as my right hand side. Okay. And this can be thought of as the field in the absence of the scatterer. So if the scatterer is not there, if I have a scatterer denoted by k squared r sitting in the background of k naught squared, and then if I have some source, and this source generates an incident field, in the absence of the scatterer, okay, only this term will be present. In the presence of the scatterer, I have this contribution due to the extra inhomogeneity, and this can be thought of as a scattered field. Okay, and in doing the Field approximation, we're going to assume that the scattered field is much, much quicker compared to the incident field. So if we assume that the scattered field is much, much quicker than the incident field everywhere, then I can say that the total field is approximately the incident field everywhere. And if this is true, then I can say that the scattered field R, which has been given by this, can be approximated by this integral. Let me call this O of r prime times phi of r prime, and this has now been replaced by the incident field. This is called the Field approximation. And this O is actually k squared r minus k naught squared. Put this. So this is called the Born approximation. And Born approximation is also called a single scattering approximation. Because what happens is that this should actually be the total field, but if you don't let this to evolve to become the total field, you just say that the field enters induced current and leaves the object. The field only has a chance to go through one interaction, which is the single scattering interaction. So this whole thing is called the induced volume current, if you want to induce volume current. The induced volume current should be this k squared minus k naught squared times the total field, but we're going to approximate the total field with just the incident field. So it's like single scattering approximation. It's like if you expand this as a Neumann series, you just pick the first one in the Neumann series. Okay. But this single scattering approximation allows you to do quite a number of mathematical manipulations that makes it look very simple and nice. Let's go through some of this mathematical manipulation. Let's assume that we have an experiment where we have an object here, and the origin of our coordinate system is there. I'm going to do this in 2 dimensions so that I use rho, and that the transmitter is going to be located here in 2 dimensions. And then this is where the transmitter is. And I'm going to measure with the receiver somewhere here. Okay, the receiver is going to be located at rho r, and this is where the receiver is. Okay. And that the object is going to be distributed and give rise to volume current. The volume currents are going to be denoted with rho prime. Okay. And if I'm in a far field, if I'm far enough, this incident field is going to come in like a plane wave. I can think of this kt as the incident plane wave for the transmitter field. And then I can think of this kt as the k vector for the plane wave that is in the other direction. If I'm in the far field, if both the transmitter and the receiver are in the far field of this object, then because they are in the far field in 2 dimensions, I can approximate the Green's function, which in this case relates. The Green's function actually relates the source location to the observation point. This is the observation point. The observation point is going to be the receiver. The Green's function is going to be this thing, which in 2 dimensions is going to be I over 4 H01 K0 rho minus rho prime with the receiver here. Okay, and if I'm assuming myself to be in the far field, I can use the large argument approximation for the Henkel function, and this would become I over 4 2 over I pi k naught rho r. Okay, rho r being the magnitude of rho, and then with the correct phase factor, e to the I k 0 rho r minus I k naught rho r. So rho prime should go here. Okay. Do you know how to make this approximation, or do I need to go over with you once again? Going from here to here. Everybody knows how to make the approximation. This is generally called a far field approximation. And what you do is that you use this fact that this x is 2 over I pi x e to the I x when x is long. And then you plug in x with this value. And in the denominator, you just replace it rho r. In the denominator, you just make this approximation. Okay, for the denominator part. Okay, so this denominator becomes this one. And then in the exponent, you have to be a little bit more careful. E to the I k naught rho r minus rho prime. Okay? You cannot replace this with that. You cannot say that this is equal to that. This would be utterly wrong. Why is this utterly wrong? This is very bad, right? This is wrong. But why is this not a good approximation? Phase, right? Phase. Even though this correction might be small compared to rho r, but it's not small compared to the whole thing. Okay, it might, when you have a phase correction, it's compared not to this whole thing, but you have to compare with the entire 2 pi. It's only if this thing is much less than 2 pi, not this much less than this. This has to be much less than 2 pi. Then only you can ignore this. If this is much smaller than this, you cannot ignore it. Okay, because of the phase thing. And this is called a far-field approximation. And usually there is a correction term to this. The correction term to that is, let's go through that correction term. Maybe make write this as this is equal to that, and then this is equal to rho r squared minus 2 rho prime dot rho r plus rho prime square, right? If you multiply this out, you get 4 terms, and these 4 terms become something like that. And we actually making an approximation that only the first 2 terms are important. And draw that quadratic form. Okay? And then you can take the square root of this now. If you take the square root of this, then you will have this in rho r square root of 1 minus 2 rho prime minus rho r over rho r squared. And then if you take another approximation, this will be rho r 1 minus. If you use the binomial expansion, then this will become this is the binomial expansion. The 2 goes away because 1 minus x to the half is approximately 1 minus half x by the binomial theorem. So this becomes that, and then this will become rho r minus, and then if you multiply things out, this becomes 1. This becomes a unit vector. That's the result. Okay, and then we are throwing out the quadratic term, and then keeping only the linear term. Then you keep the linear term, this is what you have. Okay. And this is called the far-field approximation in electrical engineering. In optics, they call this the Fraunhofer approximation. So this is far-field. And then I think you spell it like this, Fraunhofer. Depending on who you talk to, I think this is spelled different. Fraunhofer zone. Here in the Fraunhofer zone means that in this zone where this approximation is valid. But if you get closer to the source, what is that zone called? The Fresnel zone. Okay. So if this term is not dropped, you have the Fresnel zone. Okay. And then of course if you go further than the Fresnel zone, you have the Near zone. Okay, so Fraunhofer zone, Fresnel zone, the Near zone. Far field, there's a mid field region and then there's a near field region. And for those antenna designer, you have to make sure that you are in the far field zone before you can make this approximation. There's a certain limit compared to the antenna size with its wavelength before you can consider yourself to be in the far zone. So if you do antenna measurements in the anechoic chamber, you better make sure that you're in the far zone of the antenna. The larger the antenna is, the further you have to go. Because the larger the antenna is, this rho prime term is going to be larger. You have to go further away to drop this term. Okay? So there are certain things that you have to be watchful about if you're an antenna engineer. But say if you're in the far zone, then you can do this. This actually gives you something quite nice because it allows you to write things in terms of Fourier transform. I can also say that the incident field is generated by a point source. The incident field is due to a point source. If that is the case, then I can write the incident field also in terms of a Hankel function. I can write the incident field as being due to a point source in 2 dimensions. Equal to that, the Hankel function of the first kind. And if I do a far field approximation to this incident field, assuming that the transmitter is far enough, then I can also write this as I over 4, 2 over I pi k0 rho t, just like I did before. And then with the proper approximation in the exponent so that it becomes a valid far field approximation. Okay, I can also do that. Now if I plug in the Green's function and the incident field with that approximation, my phi scattered will look something quite nice. Okay, I'm going to further say that KR, the K vector that points in the R direction is K0 rho R hat. Okay, KR points in that direction. Sorry, this is KR. Okay, and I'm going to say that KT, the K vector that points in the transmitter direction in the opposite way, is defined as K0 rho T hat. Okay, now I'm going to substitute them in here and get a different expression for rho scattered. And if you get all those approximations correctly, then in the far zone, this can be approximated with something that looks like I over 8 pi K0 rho T rho R. Rho T plus rho R. Okay, and then the rest of the term that has to be in the integrand is this term as well as this term. The other terms can be pulled out of the integrand. Okay, what you have left is actually these 2 terms in the integrand. You have the rho prime, the R prime becomes the rho prime. And then you have, say, the Green's function, only this term is left in there, e to the minus I. Remember that I call this K0 rho R, KR hat. So So this becomes I K R bar, not hat, dot with rho prime. Okay, and then this term here, I will call e to the I K T bar, rho prime. Okay, because the way I define KT. And then whatever that's left is all of rho prime. So the integrand becomes very simple. It becomes very simple, and if you notice that this is just a Fourier transform, because I can rewrite this as just being equal to the rho prime e to the I. Let me see what I call it. KR minus KT. Okay, KR minus KT dot with rho prime over rho prime. That thing in the circle is just that thing over here, and this is just equal to the Fourier transform of this evaluated at KR minus KT. Okay. So it has something that's very nice. We say the scattered field is a big constant I can estimate times its Fourier transform. So the Fourier transform is at the difference of these two vectors. Okay. So I'm collecting Fourier data in the far field. If I put the receiver there and my transmitter here, I'm collecting Fourier data in this manner. But that only gives me Fourier data at one point in Fourier space. So if I want more Fourier data, what should I do in this experiment? I'm going to get that Fourier data, which is this thing over here. What can I do to improve the diversity of my Fourier data? I change the receiver location, right? If I change the receiver location, then it maps out a circle. Okay, so I can think of this experiment as being, say in one of the experiments, KT is pointing here, like this. Let me see what picture I use in my book. Maybe I use like the same picture as I use in my book. So don't get confused. Okay, so if KT is pointing in that direction, then minus KT is pointing in that direction. And then KR plus minus KT is pointing in that direction, say KR, this is KR in this picture over here. And so if I change the receiver location, I will map out this Fourier data. So if I fix the transmitter location and just change the receiver location, I'll map out the Fourier data on that circle. Right? So if I want more Fourier data, I change my transmitter location to another place. Okay, change it, rotate this slightly. I will have another circle, right? I change my transmitter location, another circle, and you can see that. Finally, I map out all my Fourier data. I will have a big disk of Fourier data in 2 dimensions. And I can interpolate those Fourier data to a rectilinear grid and do an FFT. And then get this object back. Okay? That's called diffraction tomography. It's based on the fact that the far field is a Fourier transform of the object function. But transform of the object function according to this manner, the difference between these two K vectors. The K vectors of the transmitter and the receiver. So it's not as nice as slice projection theorem, but it's still very nice. It's still very nice. So then the trick is how to design experiments that allows you to collect this Fourier data. And this theory is based on single scattering approximation. The tree just enters the object and leaves immediately without multiple bouncing. With multiple bouncing, then the expression is a lot more complicated than this. And what is the radius of the big disk that this Fourier data collects? Or if you do this experiment by rotating the transmitter 360 degrees around the object, the receiver also 360 degrees, you map out, or you fill in the disk. What is the radius of the disk? 2K. And that determines the resolution. Okay. The resolution is wavelength limited. Because this disk is 2K naught. You can have no Fourier data outside this disk unless you do some signal processing by extrapolating or something outside this disk. Assuming certain analyticity about the Fourier data and extrapolate outside this disk. And if you were to just Fourier transform back according to this disk, your resolution is determined by 2K naught. And I think that corresponds to either lambda over 2 or lambda over 4. It is almost like the Rayleigh limit. But Rayleigh limit is often talked in terms of lenses, but we're not doing a lensing system over here. Aperture can be infinitely large because we can collect data from all over the place, all around the object. Okay, so the aperture is actually can be as large as you want. It's not determined by the lens size of the camera. So in the lens size of the camera, the Fourier data is limited by what is called a numerical aperture. You learn a lot about aperture, antenna aperture, synthetic aperture, and also radar cross-section. All those things have something to do with cross-sectional area. But there's another aperture that you have to learn called the numerical aperture, the optics people use. Okay. The numerical aperture of a lensing system is just that. The numerical aperture is just a single. Okay. Actually, it does not have, it's the dimensional thing. There's no dimension, but the optics people call it the numerical aperture. The larger the numerical aperture, the better it is. You collect more Fourier data. Right? You know. The lens is a Fourier inverse transform device. Everybody knows that. The lens is a Fourier inverse transform device. So when the light scatters off you, over here, I'm actually looking at your Fourier transform. With my lenses in my eyes and my eyeglasses, that are doing the inverse Fourier transform to convert you back into an image. So if I take off my eyeglasses, I cannot perform a perfect inverse Fourier transform on you guys. So I see some fuzzy images because of the fact that my lenses are no good, just like many of you. You're wearing glasses, right? We have imperfect Fourier inverse transformers in the eyes because we study too hard. Okay. So we don't have to Fourier inverse transform with the lens for this kind of system. We can Fourier inverse transform with software, as long as we know how to collect the data and put them on tapes, and then realign them so that we can do signal processing with them. And in the case of the synthetic aperture radar, you collect data using a different notion. Again, I only know this approximately. I don't know the fine detail. There must be a lot of technology that goes in the detail of implementing the synthetic aperture radar system. So one way is assume that the airplane is flying towards you. This is called a side-looking radar mode. So you send out a radar, and then it hits the terrain, and then it has an echo. Maybe the terrain is not that bad. The terrain is just maybe slightly undulated. It will come back with an echo, but you hit the ground with a broadband signal so that you send out a pulse. You can send out a CW signal. So you can do time gating to get rid of multiple scattering. So only the first arrival is taken care of by time gating. So time gating allows you to make one approximation on the data, or single scattering approximation on the data. And then because you can make single scattering approximation, the scattered field is a Fourier transform of the surface object, the scatter, okay? And then, but the radar has a swath of a width. It's not narrow beam, so it actually looks at a certain areas and then looks for echoes from there. Okay, and then it does a broadband signal so that your K vector is not restricted to a fixed length. So your K vector can have a certain length, maybe a certain bandwidth. Okay? And then you look at the data at a different angle, depending on where you are. And then if I take the top view of the airplane, the airplane also have a width that looks something like that. So it looks at the thing at different angle due to the thing that you can sweep this way. You can also sweep this way. So every given spot is looked at with different angle. This is a side-looking radar. And then you can fly the airplane over the same path, okay? So they fly in the same path. And then they will collect the synthetic data of the same spot with different look angles and different frequencies because of the bandwidth of the radar. Okay? After they have the reflected data from a given spot with different look angle and different bandwidth, they can do signal processing to get back the object. Okay? There's one thing. You do time gating to get rid of multiple scattering. This is a side-looking radar. And then there's another one called the spot-looking data. I think in that case they fly the airplane in the circle. I think it's called spot-looking airplane. Spot. They just look at one spot and then just fly the airplane over. And then they can get high resolution image of that. Why is it called synthetic aperture? Because you are actually not using the real aperture of the antenna on the aircraft. The antenna will be rather small compared to wavelength. It will have terrible resolution if you just use the aperture of the antenna. Instead, you fly the airplane over in space, and you will create a very, very large aperture, just like if we have the experimental facility available to ourselves, we can collect data from all around. We are not limited as in the lens optic people by the numerical aperture. You can look at this thing from all angles, and we have much higher resolution than the lens people. Okay? And then because you can fly the aircraft over the same domain by different lines, and then registering those data correctly, you can piece all those data together and get a beautiful image on the surface of the Earth. Yes, you have a question?
So, like at each plane location, you're getting, because it's a broadband pulse, you're like in that circle, in that disk
Right.
picture, you're getting a thin,
Right,
thin
right.
sector of that circle.
Right, right. That's a good point. That's a good point. You're actually not getting full Fourier data like I showed in that thing over there. Most likely than not, you have different look angles. Say you only have a certain Fourier window. You only have Fourier data here. Okay, because of the bandwidth, you can change the K vector. Because the different loop angle, you can change this K vector, right? And most of the time, your K vectors are not as free as we have in this experiment. KR and KT almost point in the same direction because you have to look for echoes. KR and KT are not as nice as this picture over here. So KR and KT are pointing almost in opposite direction to each other. So because they point in the opposite direction to each other, KR and KT will add up to something, and you only have a small degrees of freedom to change them. So most likely than not, you have a Fourier data that looks like this. You don't get